I am Anil Kumar. Welcome to my series on Newton's second law of motion. We'll consider some concepts in this particular video. In case you want to learn from me, you can always write an email on the address given. Here is our website to check for the latest updates. So we'll begin with understanding what is Newton's second law of motion and how does that law help us to figure out whether a system is in equilibrium or it is not in equilibrium? Well, Newton's second law relates mass and acceleration. We'll look into free body diagram since that is a must to solve any question related with these kinds of applications. We'll take an application which is extremely common. Every day you go for grocery and hold this card in your hand. Now that reminds me that this is kind of an experience which you really get. So let's talk about it and understand that in our daily lives, how does it touch upon what we are learning? Newton's second law of motion, right? So we'll take up three examples, and with these examples, we'll understand how should we apply this law, when is the system in equilibrium, when it is not in equilibrium, how do we find the acceleration, and these applications will then help you to solve questions in your book. Perfect. So basically, we'll take a card, we'll move it on a horizontal plane, on an inclined plane, and with different conditions, we'll see how should we solve such questions. Correct? I hope that is interesting. Let's begin with first understanding the law itself. So Newton's second law of motion, what does it say? Says the acceleration of an object is directly proportional to the net force acting on it and is inversely proportional to its mass. So acceleration of the object, which I'm writing with A, is directly proportional to the net force. Net force means sum of all the forces at that point, correct? So for example, if we're considering a point where the forces could be in different directions, we'd like you to resolve those forces into the x components and into the y components, correct? So once you do that, after that, you can actually add them up. For example, there could be more forces, right? So what I'm trying to say here is if we have a force kind of like this, now this force could be resolved into x and y components in this fashion, correct? So you can make a triangle or a parallelogram and then resolve it. So once you resolve this, you get all the forces in x and y direction, correct? Let's take up another force. For example, a force which is kind of like this can be resolved in these two components. So once you resolve all this, then sigma of fx will give you the components in the x direction and sigma of y will give you components in the y direction, correct? And then you can find the resultant F, you can say net force, correct, from these two forces. Also, you can find the angle from these two forces. You get the idea, correct? So you have learned all this. This is kind of a summary. Anyway, we'll take a few examples in which the concept will be clear. So basically what we are trying to say is acceleration is directly proportional to this net force divided by the mass, right? Therefore, we say inversely proportional to the mass, right? That is what acceleration is. You could rearrange this particular equation and write that the net force results into the acceleration of the body, correct? So if it is acting on a body, in that case, if the net force is positive, there will be acceleration, right? Non-zero, I could say, because accelerations can be negative also. For example, applying brakes is a negative acceleration, results into, right? Okay, now it's a matter of direction which gives you positive or negative. Magnitude of acceleration will always be more, correct? Mass is a constant. So from here, you see that if the force, net force, is non-zero, then we have acceleration in the system. So that gives you what? Well, let me consider this. Anil moves a cart with mass of 15 kg at a constant velocity. Now, when I say that, do you think this represents equilibrium or non-equilibrium state? So we need to consider this particular statement. And the question for you is, Anil moves a cart with mass of 15 kg at a constant speed. Now, what does this represent? It is saying that the acceleration is zero, right? Constant speed means no change in speed, and that means no change in velocity, and that means constant acceleration, correct? Zero acceleration, right? Okay. So Anil moves a cart with mass of 15 kg at a constant velocity. It means what? It means that cart is moving at a constant velocity. Means what? Acceleration is therefore zero. So when we say that constant velocity is involved, in that case acceleration is zero, correct? So if acceleration is zero, then F, the net force, will be also zero, right? So the net force is also zero for constant velocity case. That is the state of equilibrium. Because the system is in equilibrium as the net external force is zero. So we have related the system status, whether it is in equilibrium or not. So equilibrium means that the net force is zero and the acceleration of the body is zero. So when I say acceleration of the body is zero, it means the body is at rest or is moving at a constant velocity, correct? So system is in equilibrium means that the object is at rest or moving at a constant velocity. You understand? So only then the system is in equilibrium. Otherwise, it is not in equilibrium and will have an acceleration, okay? So I hope this concept is clear and it's absolutely clear how second law makes us understand this concept. Now let's take these questions one by one. Here is our very first example where we'll talk about stopping distance of a car. So to give you a background, what I learned is that in the stores, people just push the carts and they sometimes release it. The carts could actually bash on the racks and on the arrangements which they have made in the store and can provide some damage. And therefore, it's kind of necessary that we have some friction with the um, cart wheel and the floor so that it doesn't really go very far. Well, it will be an exercise for people to use such carts. They may not like it, but from the safety reason, it is kind of important, right? Especially when kids are around. Okay, now let's look into the question itself. It says, a grocery store wants to purchase cards for the store with maximum 1.50 meters stopping distance when it is moved at 2 meters per second on the horizontal floor. Find the minimum effective coefficient of friction between the wheels and the floor to meet the objective. So that is the question for us. So here we want maximum stopping distance of 1.50. So when I say 1.50, see here, we are talking about three significant figures, right? So we are talking about three significant figures. We need to write down all our answers to three significant figures, okay? When it is moving at a velocity of 2.00 meters per second. Another three significant figures given to us on a horizontal floor. Find the minimum effective coefficient of friction. So this cart will only stop because of the frictional force, right? So if you move the cart, then there is always a force which is acting in the opposite direction, and this is what we call the frictional force, correct? So that is to say, when we are trying to move the cart in this direction, right? So when you apply a force in this direction, maybe a push, for example, in that case, and if you release it, right, in that case it comes to a stop because that force becomes zero and there's a frictional force which is acting in the opposite direction and helps to stop the car. So because of this frictional force, we have coefficient of friction, correct? Normally, coefficient of friction is mu into F of normal. That is related to the mass of this particular card, right? So we'll understand how do we relate these things. Okay, now let's see. First thing is, of course, we should draw a force diagram in this particular case. Now, can you tell me how do we sketch a force diagram in this particular case? Well, as I was saying, on the floor itself, let's say this is the floor, right? So on this floor, the card is there. So we'll represent the card with just a point, and this point exerts a force which is downwards equal to the mass mg of the card. Now, card could be loaded also, it doesn't matter. But in the first case, we are taking just empty card. So let that be the mass. And that force exerts a force which is in the opposite direction. And that is your force, which is we are calling F of normal. Now, these two forces cancel each other, they are equal and opposite. However, since there is a friction here, there is a frictional force which is F of F, and this frictional force is mu times the normal, right? And the card is in acceleration since it is moving at 2 meters per second and it wants to come to rest. You get the idea, right? So it is acceleration is there, and therefore we have a forward force here, and that we are calling as as some force F right now. When you release the card, say grocery store, and we say find minimum effective coefficient of friction between the wheels and the floor to meet the objective, means the card comes to rest when the force is released, right? So when F becomes equal to 0, in that case, since the movement was already there, correct, initial velocity was 2 meters per second, after some time it is going to come to rest, correct? Since there is a frictional force acting in the opposite direction. Now this is opposite direction. Is that clear to you? Since it is opposite direction, we'll take this force as a negative force. Perfect. So that becomes the situation. Now, in our case, what we have done here is we have used Newton's second law to get to our equation, right? So let's look into this. The vertical force will cancel out for the cart moving on the horizontal flow, right? As you can see, F of n is equals to mg, right? So we can write F of n is equal to mg. Now, force of friction is the net force that will stop the cart. So when you release, that means when that external force has been released, when the cart is released, in that case it comes to a stop. And so we can now apply the Newton's second law, which says that the acceleration is the ratio of force to the mass, right? So in our case, the force is the mu times mg. Sorry, I forgot to write mu here. Force is mu. This is okay. Fn is okay. Force, frictional force is mu times mg. Here we have written that, right? Frictional force is mu times mg. So frictional force, which is mu times mg, has been written on the numerator with the negative sign divided by m. And as you can see, the mass m cancels, correct? So the mass cancels. We are left with minus mu g. So the acceleration is basically because of the frictional force. And it is equals to minus mu g. You can also see that this acceleration is independent of mass, right? So we notice that this is independent of mass, correct? So we see that this expression is independent of mass of the card, correct? Now let's talk about the stopping distance. Getting back to the equations which we have learned, right? Especially when we're talking about the acceleration, then we have v square minus u square equals to 2as, where v is the final velocity, u is the initial velocity. We just found that the acceleration is minus mu g. We are given that the initial velocity is 2 meters per second. Final velocity at rest will be 0. And we know that we want a stopping distance of 1.5 meters. So substituting these values in the equation v square minus u square equals to 2as, after rearranging, we really want to find what mu is, correct? So what I did here is we came up with the general formula. So it's a good idea to look into the general formula, which is right there. So I actually derived the formula from the given situation and then substituted the value. Final velocity being 0, so 0 minus 2 square, which is the initial velocity, g taken as 9.81, and the distance given to us as 1.5. On calculations, we get 0.1359, which is rounded to three significant figures. Is that clear to you? And the coefficient of friction in this particular case is 0.136. Remember, coefficient of friction is a constant, okay? We round it to three significant figures as shown here. So once again, important thing to note here is that the stopping distance is independent of the mass of the car. So I hope this concept is absolutely clear to you. So it directly comes from the Newton's second law. The state in this particular case, we say, is in equilibrium to begin with. When we are constant velocity is applied in that state, we are now changing into a state where acceleration. So once you release that force, then it is not in equilibrium. There is an external force, which is the frictional force, and this frictional force brings the object to rest. That means there is negative acceleration, right? There is negative acceleration. And so we get this equation from the Newton's second law. Net force acting is negative frictional force divided by the mass, and then using one of our equations of relating acceleration, velocity, and distance, v square minus u square equals to 2as, we can find the frictional force. Is that clear to you? Correct. So we're done with the first example, found this frictional force coefficient, right? Okay, let's take up the next example here. So in the next example, I've taken the same store, same type of things, very related. We'll now talk about angle of inclination and how do we work with similar situations when object is moving along an inclined plane. Okay. Now, a card in a grocery store has the effective coefficient of friction between the wheels and the floor as 0.136. Just calculator. We use the same value. A ramp is designed to hold the empty cards. What can be the maximum slope of the ramp so that the cards stay in their position when left on the ramp? So as you can see, to do the parking, we might use the ramp. It gives you slightly more area, right? So, and then once you hold them here, in that case, you can, it's easy also to take them out. So sometimes we use slopes to hold them. And the frictional force helps us to provide a ramp in a way that they don't really roll out on their own, correct? So that's kind of important and interesting to see. So we'll look into this design. So basically, to solve this question, first thing, of course, is to draw a force diagram. So we have shown a ramp shown here, and we have used a point to represent the mass of the card at a point, right? That is how we do it. And now the weight is acting downward, shown by W. Now, since the inclined plane is there, the normal is always normal to the inclined plane, correct? So the normal is always normal to the inclined plane. So that is 90 degrees to the plane. Now this normal is against a component of W, which we are resolving along the edge of the inclined plane and the normal. So writing W as W sine theta, the component along the side of the inclined plane, and W cos theta is along the normal. So if that is the angle theta, in that case, since this is right angle triangle, that will be the angle of theta, right? And so W cos theta is the component which is opposite to the normal, and W sine theta is the component which will push the card down, right? So that is the component external force being applied to bring it down. Now, as soon as this force is being applied, the wheels, they have a coefficient of friction, so that friction is being seen in the opposite direction. Friction should be higher or maximum equal to this so that it is in equilibrium or in a state of not moving, right? Net force should be zero, correct? That's the whole idea. Okay, so in the given situation, what you could do is you can say that the x components and the y components are zero, right? So you can say the net force basically is zero, means that you need to find the x components. We'll say x components are along the direction of the inclination. So let me write those as x. So we'll write this as our x components, and these are as y components, which is normal, okay? As that should be 0, and then sigma of y should also be equal to 0. So that means these two forces should be equal, correct? So we get our, and this force also should be equal, correct? So we get two equations right there. F cos theta equals to f of n, and f sine theta is the net force here, which is frictional force, uh, is equals to the frictional force along this direction. Correct. So we have these two equations. Now, what is the frictional force? Frictional force is always mu times the force along the normal. Correct. Fn. That is what the frictional force is. Now, from here, we know what Fn is. We could substitute that and then solve the equation. But what I did was kind of direct. I just divided one equation by the other. Correct. So we have this equation as equation 1 and this equation as equation 2. So when I divide equation 2 by equation 1, so we get what? We cancel out the W terms, right? Sine theta over cos theta is equals to f of n mu f of n, right? So mu f of n and f of n. So f of n cancels and W cancels. We get sine theta over cos theta, which is tan theta, is equal to mu. So directly we can find the value of mu, which is tan inverse of the, the coefficient of friction, and which is 7.74 degrees. You get the idea. So that is how we get the maximum angle theta in this case, and that works out to be 7.74 degrees. Is that clear to you? So you could have a small inclination in this store, and that will not, that will keep the cards uh, out of rolling down. You understand? So that is how you could store them. So I hope you find this interesting and useful. So now let's move on and see some more examples of a card in a store. Here is another example. So what will you do? When you go to the store, should you pull the card or you push the card? So that is the question which we are going to answer now. Push or pull a card? Question based on this is, the cards in a grocery store has the effective coefficient of friction between the wheels and the floor as 0.136. Anil moves the cart with constant velocity of 1.50 meters per second with load of 20 kgs. Lot of grocery, right? What force is required if he pushes the cart at an angle of 30 degrees below the horizontal? So we're talking about 30 degrees below the horizontal, and pulls the cart at an angle of 30 degrees above the horizontal. So these are the two cases, right? So we are talking about push, which is we are saying case 1, correct? And then pull, which are saying case 2. What do you think is better? Either push or pull, right? So most of the time people are pushing the cards, but at the end of this video you will learn that pull could be better, right? So we'll actually now begin with a body diagram. Okay, so this is the FBD for us. Now you can see that the cart is right there represented by a point. Now at this particular point, what are we doing? We are applying a force at 30 degrees to the horizontal. So that is the force being applied 30 degrees to the horizontal. Now this particular force can be resolved into two components, the horizontal component f cos theta and the vertical component f sine theta. Now you can see that this vertical component f sine theta is along the weight of the card itself with the load, right? Now, this card is staying here. The force which is acting downwards due to gravity is mg. And so we have a normal, which we sometimes write as Fn, which is equal to mg, right? So up, down forces are equal, right? So we know that mg is equals to n. Frictional force is always there since we have a coefficient of friction which has a value of 0.136. So therefore, we have a frictional force mu times n. This is important to understand always. frictional force is mu times n. So that is the case which we are looking into. But when you pull the card, in that case, what happens? We are applying a force 30 degrees to the horizontal in the direction shown. Now, in this case, you will notice that the vertical component of pulling force opposes the weight of the card, right? So, therefore, it should help you to pull. You get the idea, correct? Rest of the situation is almost similar, correct? Now let us see how do we solve this. We have a force diagram here. I'd like you to pause the video at this stage and get the answer, okay? So let's look into the two cases. So one, if we are applying a force which is push at a 30 degrees, we'll use the first case, which is 30 degrees below. And in that particular case, you can resolve the components. The x component is force of friction, which is mu n, and n is equal to the, okay, so Fn is equals to F cos 30 degrees. So force of friction is equals to F cos 30. But another equation is that we know that force of friction is mu times N, and therefore I wrote this in between. Correct. Now what is N equals to? N is equals to mg and the component, which is F sine 30 in the vertical direction downwards. So that is the value of N. Replacing N with the value mg plus f sine theta, we get the equation that mu times mg plus f sine theta equals to f cos theta. Now from here, we can rearrange, taking the mu components, f components together, f sine theta, right? And then we have f cos theta. So taking f sine theta to the right hand side with mu multiplied to it, we get f cos theta minus mu f sine theta equals to mu mg. Now since f is a common factor, we can actually get f as mu mg divided by cos theta minus mu sine theta. You get the idea. So that is how you can derive your force. So I'll actually like you to pause the video, do this derivation, right? So redo and confirm your answer and write down this formula for the case when we take a case of a push. You understand? Very important. And kind of important thing here is to see the denominator. Cos theta minus mu sine theta. Now we know the values. Substitute the values given to you, correct? All the values are given to you. Just substitute them and then get your answer, correct? You do get that the force should be 33.4 newtons, correct? So that is how we are going to solve this particular question. Now let's look into the other case, which is pulling at an angle of 30 degrees. So when you pull at an angle of 30 degrees, in that case, as shown in this diagram here, the two components, one is along the x, the other one is along the y direction. And that sine theta component actually opposes the weight of the card. Do you see that? And therefore, the net force is slightly helping you in forward movement, correct? So frictional force in this case will be mu times n, as we know, and is equal to the force F sine cos theta in the other direction, right? So equating the sigma, we are looking into the forces along the x direction, and now let's look into the forces along the y direction. So in that case, n plus F sine theta equals to mg, correct? Let me rewrite this. So we have F equals to N equals to F mg. Now, so from here we can isolate what N is, right? So let me just write here. So N is equal to mg minus F sine theta, correct? Okay. So we'll rearrange and write what is the value of N. So N is mg minus sine theta. We're substituting this value of N over here. Mu n. You get the idea. So mu times mg minus f sine theta is equals to f cos theta. So we rearranged and wrote our equation. Perfect. Once we've done that, open the bracket as we did earlier, open the bracket and then rearrange. So you get mu mg as one of the components and mu f sine theta as the other components. So we're taking the mu f sine theta on the right hand side and written this as f cos theta plus mu f sine theta, and that should be equals to mu mg. Correct? Taking f common, we get f times cos theta plus mu sine theta equals to mu mg. And this time, we get in denominator cos theta plus mu sine theta. You get this idea, right? So we get the denominator with plus value of cos theta and mu sine theta. When you were trying to push, it was negative. Do you see that? So that makes all the difference. Substituting the values which are known to us, we get the value of force being applied as 28.6 newtons. Correct? So remember, in push, we found the force to be 33.4 newtons, and now, while pulling, it is only 28.6 newtons. There is a difference of around 5 newtons of force in just changing the direction. It's very important, therefore, to understand that when you are pulling and pushing the card, you're applying different amounts of force, and it is always better to pull a card. Perfect. So that illustrates the same thing. So I hope you have understood many concepts which we took only with a simple example, a simple card in a stove. And we have seen how different kinds of questions can be solved with this particular example. I hope you find it interesting. In the next video, we'll actually consider different cases. We'll talk about two masses being attached by a string. Now, these masses can both be on a table, can one be on the table, the other one hanging, or both be hanging with a pulley. In that case, we'll find acceleration and the tension in the string. This summary gives you the solutions for those conditions in a tabulated way, which will help you further to do your exercise. So watch this next video also along so that you get all your concepts right. Thanks for your time and all the best. Feel free to write a comment, share your views, and if you subscribe to my videos, that'll be great. Thank you once again.